Hey there guys, we're working on day 3 of thermochemistry. Today we're going to do specific heat calculations. Not hard, definitely think it's something that you can do. I have the document camera going down here so I can work along with you when we get to those slides that need working on. So specific heat is the amount of heat that's needed to raise the temperature of 1 gram of substance 1 degree C. Everything has a different specific heat. Specific heat is a physical property, and you can observe specific heat without changing the molecules of the substance at all. Okay? As I said, everything will have a different specific heat. The unit for specific heat, it looks like a strange one, but just wait till you get to physics and you'll have some really strange units. This is J/G degrees C. So this is joules per gram degree Celsius. The specific heat of a substance is an intensive property. That means no matter how much you have, that specific heat will never ever change. Okay, specific heat of water never changes, specific heat of silver never changes, specific heat of gold, specific heat of everything. Specific heat doesn't change no matter how much you have. Having a low specific heat means that that substance can heat up faster, but it can also lose heat faster. Sand heats up really fast compared to water, believe it or not. Water has a pretty high specific heat, 4.18 joules per gram degree Celsius. That's pretty high. So we've got some specific heats here. So water's up here at 4.18 joules per gram degree Celsius. Then we've got aluminum at 0.902, wood at 1.674, iron at 0.450, and gold at 0.129. So the question is, on a hot day, which one gets too hot to touch first? Yeah, the one with the lowest specific heat. That would be gold. Gold would get too hot to touch first. Then would come iron, then aluminum, then wood, and finally water. So the cold wind comes by. Which one of these things cools off first then? Right, it goes in the same direction. Gold will cool off first. It both loses and gains heat faster than everything else. So gold would be cool off first, then iron, aluminum, wood, and finally water would lose its heat the fastest. So our specific heat formula, you guys love math. When we have math involved, you guys are all good. Our specific heat formula, Q, is heat. So Q is heat energy, and its unit is joules. That's the unit for energy. Okay, so Q is equal to M, which is mass, and that's going to be in grams. C is our specific heat. And then delta T means the change in temperature. It's the final temperature minus the initial temperature. Okay, so that's our formula. Q equals MC delta T. Sometimes it's called Q equals MCAT. Right? So calculating this is not really all that hard. I think you guys will enjoy it because it's pretty easy to do. Q is the energy lost or gained during the reaction. It's energy. Okay, it can be positive, it can be negative, and the unit will always be in joules. Delta T, what is delta T? Well, it's the change in temperature. It's subtraction. For example, a pot of water is heated from room temperature, which is 25 degrees C, to just before boiling at 99 degrees C. What is the change in temperature? Remember to do final temperature minus initial temperature, 72 degrees. Okay, that's our delta T. Pretty easy. So here's where we're identifying units. I was going to follow along with you. So what we have here, joules per gram degree C, this is specific heat. Get my pen to work. Okay, specific heat. And what's the unit, or what's the symbol for that? That's going to be C. 200 grams. Y'all know what grams are. That's mass. And symbol, in our problem, it will be symbolized by the letter M. Joules per gram degree Celsius, there's specific heat again. And its variable symbol will be C. Joules, what is that? It's energy. Okay, and energy in our formula will be Q. Okay, number 6. 21.5 degrees C. That's temperature. And its symbol will be T, or delta T, if we've already calculated the change. Joules per gram degree Celsius, we've got specific heat again. And that will be C. 14.1 degrees Celsius is temperature. And it will be T, or delta T. 13,000 joules. Joules is the unit for energy. And energy will be represented by the letter Q. And finally, 98 grams. Grams is mass, of course, and in our formula, the variable will be M. Okay, so this is a neat video, and she's really good at explaining, so we'll do some of these problems after you hear her explain. Notice how she uses color to box her givens and circle her unknowns, so follow along.
The main formula you will see in calorimetry is referred to as Q equals MCAT, where Q is heat measured in...
Okay, my speakers were off, kids, so let's see if this will work for you.
The main formula you will see in calorimetry is referred to as Q equals MCAT, where Q is heat measured in either kilojoules or joules. M is the mass measured in grams. C or CS is the specific heat capacity. Its unit is joules per gram Celsius. And our delta T is the change of temperature, which is our final temperature minus our initial temperature, which is measured in Celsius. It is important to check that all of your given values are in the specific units before plugging your values into the formula. This page, along with others I use throughout the video, are part of my 50-page guide on thermochemistry, which has everything you need to know about thermochemistry and calorimetry, including common test questions with step-by-step answers. So if you'd like to get this guide, you can find the link in the description box along with other helpful resources. Now let's do two different examples, one finding heat and the other finding specific heat capacity. Example 1. The specific heat capacity of lead is 0.129 joules per gram Celsius. Find the amount of heat released when 497 grams of lead are cooled from 37.2 degrees Celsius to 22.5 degrees Celsius. Let's identify what we're given and what we're finding. We are given our specific heat capacity, our mass, and our initial and final temperatures. From and to are our key words here. From means that's our initial temperature, and to means that's our final temperature. We are finding the heat released. The fact that this says released means our answer will be negative. Since everything is in its proper unit, we will start with step 1, which is finding our change in temperature. Our change in temperature is our final temperature minus our initial temperature. When we do this, we get negative 14.7 degrees Celsius as our change in temperature. Step 2. Plug everything into the formula. Here's the formula we will use. We have our mass in grams, specific heat capacity, and change in temperature. Multiply all of these together and our units of grams and Celsius cancel out, and we are left with heat in joules. Make sure to round to 3 sig figs. Now, we could have written our answer as negative 942 joules, or we can write it without the negative, as long as we put 942 joules are released. Both answers are correct here. Example 2. When a 120 gram sample of aluminum absorbs 9,612 joules of heat energy, its temperature increases from 25 degrees Celsius to 115 degrees Celsius. Find the specific heat capacity of aluminum. Let's identify what we're given and what we're finding. We are given the mass, our heat, which is positive since our key word here is absorbs, from 25 degrees Celsius means this is our initial temperature, to 115 degrees Celsius means this is our final temperature, and we are finding the specific heat capacity, which has a unit of joules divided by grams Celsius. Since everything is in its proper unit, we will start with step 1, which is to find our change in temperature. Final minus initial gives us 90 degrees Celsius. Step 2, plug everything into the formula. So we know our heat, our mass, and we are looking for the specific heat capacity. And we just found our change in temperature. So multiply these two values together so we get this new value with our units of grams Celsius. Now to get the specific heat capacity by itself, we will divide both sides by this value. And our specific heat capacity is 0.89 joules per gram Celsius. For more help with calorimetry or thermochemistry, make sure to check out my thermochemistry guide, which is right over here. I know that can help shorten your study time and get you a better grade. And make sure to check out the description box for all of my other recommended resources like homework help and online tutoring.
All right, so let's see if we can't go to our next slide. Oh, nope. Let's try this. If we can go to our next slide. There. All right, so here's our example problems. I will, of course, do a couple with you. But these first few, just going to go through pretty slow. I'm going to help you when we get to these other problems. Example problem number 1. A 12-ounce can of soda weighs about 450 grams. How many joules are released when a can of soda is cooled from 25 degrees to 4 degrees? The specific heat of liquid water was given to you, 4.18 joules per gram degree C. So let's label what we've got. Okay, I have my mass, 450 grams. Initial temperature, because that's a from 25 to 4. So 4 is my final, 25 is my initial. So what's the change in temperature? It's always going to be final minus initial. So it's negative 21 degrees C. Okay, Q is what we were looking for. We'll go back. Q is what we were looking for. And C is our specific heat, which was given to us 4.18 joules per gram degree Celsius. So when we put that in our formula, Q equals MCAT, or Q equals MC delta T, Q equals M, mass, C, specific heat, delta T, change in temperature. So when you do all that together, you come up with negative, and watch the negative, guys, 39,501 joules. Okay, example problem number 2. I'm going to do this one with you. I got the paper down here. Example problem number 2. How many joules are required to heat 250 grams of liquid water from 0 degrees to 100 degrees? The specific heat of liquid water is 4.18 joules per gram degree Celsius. So let's see what I got here. I've got grams. Okay, so there's my 250 grams. Here's my delta T. I go from, my initial is 0, my final is 100. So my change in temperature, final minus initial, is positive 100 degrees C. Specific heat, we're given right here. I forgot to box that one. Temperature also. Specific heat, 4.18 joules per gram degree Celsius. So the formula, Q equals MC, change in temperature. I'm going to plug in all my variables here. I'm looking for Q. Mass is 250. Specific heat capacity, 4.18 joules per gram degree Celsius. And my change in temperature, 100 degrees C. So I have everything that I need for that problem. I'm going to do that math. See if we can get the calculator in here. You can see it. So 250 times 4.18 times 100 gives me Q equals 104,500, and the unit for energy is joules. Okay, example problem number 3. We have this one right here. When a 120 gram sample of aluminum absorbs 9,612 joules of energy, its temperature increases from 25 degrees C to 115 degrees C. Calculate the specific heat of aluminum. Okay, well this time I'm looking for the specific heat of aluminum. Okay, so this C is going to be what I'm looking for. I have 120 grams, so there's my mass. Initial temperature, it says that it increases from 25 to 115. So final minus initial gives me 90 degrees C. And now I've got Q. Joules. Joules is Q, so this is 9,612 joules. The formula is still Q equals mc delta T. Okay, you can plug all your variables in and then solve for the one that's missing, or you can rearrange it. I do like to rearrange it, actually. If I want to get C by itself, because that's what I'm calculating, I'm looking for C, I'm going to divide by mass times change in temperature. When I do that, mass, change in temperature cancel. So I divide both sides by mass, change in temperature. So my formula is going to be specific heat capacity is equal to energy divided by mass times change in temperature. So let's see what that gets us. C is what I'm looking for. My Q value was 9,612 joules. My mass, 120 grams, times delta T, change in temperature, which was 90 degrees C. Let's see what that gives me. 9,612 divided by 120 times 90. 0.89. Specific heat capacity of aluminum, 0.89. And what's the unit for specific heat capacity? Got it right there. Joules per gram degree Celsius. Awesome. So let's go on to the next one. Okay, example problem number 4. The temperature of a sample of water increases from, let me put that in there, from 20.8 degrees Celsius to 40.6 degrees Celsius as it absorbs 5,650 joules of heat. What is the mass of the sample? Okay, so I've got a delta T here. I'm going to have to calculate my change in temperature. I have my Q value, my energy. I'm looking for mass. And it says that it's water. It's water. The specific heat capacity of water, a couple of slides ago, 4.18 joules per gram degrees Celsius. So we do have that. We'll go ahead and fill that in. 4.18. Okay, mass is my unknown this time. Initial temperature, 20.8 degrees. Final temperature, 40.6 degrees. I subtract initial temperature from final, so it's final minus 20.8. 40.6 minus 20.8 gives me a change in temperature of 19.8 degrees C. My Q value is joules, so it's 5,650 joules of energy. All right, partway there. We've got our variables. We will be solving for mass. So my formula, Q equals M times C times change in temperature. I'm going to rearrange to solve for mass. If I want mass by itself, I'm going to divide by C delta T, which means those will cancel. I also have to divide this side by C delta T. When I do that, I get mass equals Q divided by C times delta T. So let's plug variables in for that formula, shall we? Q is 5,650 divided by specific heat capacity of water was 4.18 joules per gram degrees Celsius times my change in temperature. My change in temperature was 19.8. Go. Close that parentheses. And let's do that math. 5,650 divided by, open the parentheses, 4.18 times 19.8. Close the parentheses. 68, let's see. How many sig figs can I have? 1, 2, 3. Yep, 3. 68.3. We were looking for mass, so what is that? Right, it's grams. 68.3 grams was the specific, or was the mass of the sample. So good luck, and next will be Hess's Law. we'll do that last.